let's go back to 3.2 and talk about a few of these things, such as the power functions, and let's talk a little bit more about the end behavior and do some examples from there. So, did you guys fill out these exponential properties in your workbooks? Do you have those filled out? Right. Let's fill those out now then. Um, you may have seen these before. Um, it says recall, so I'm expecting you've seen these before. When we multiply two expressions or two terms with the same base and same or not same exponents, we're going to add those exponents. So a to the n times a to the m is going to end up being a to the n plus m. So we multiply terms with the same base, we add the exponents. Similarly, if we divide two terms with the same base, we're going to subtract the exponents. So it'll be a to the n minus m. If we raise a number to an exponent and then raise that to another exponent, those exponents will multiply. So a to the n m, so n times m. Whenever you see a fractional power like 1 over something in the exponent, that's going to signify a square root. Sorry, not a square root, but a root of a, where the power of the root, or oops, oops, the index of the root is going to be that denominator n. We all should know that anything to the 0 power is 1, so that one um, doesn't matter what the base is. If the exponent is 0, then the answer is 1. Next, we have a couple of terms multiplied together, and then that product is raised to an exponent. What we can do is we can kind of separate this by taking the exponent and putting it on each of the individual factors inside the parenthesis. And when it comes to division, we can do the same thing. If we have an exponent on a fraction, we can place the exponent on the numerator and denominator separately. A negative exponent, a to the negative n, will make the term its reciprocal, so 1 over a to the n. In other words, it will move the term to the denominator if you have a negative exponent. This fraction one is kind of similar to the one on the left side where we have a to the 1 over n, except the numerator will be an exponent and the denominator will be the index of the radical. So we still have a radical in this case with the index n, but we have a to the m. The m is the exponent. Or we can actually do this in two different ways. Or we can do the radical with the index n, so the nth root of a, and then have the exponent on the outside. So the order in which we do those, taking to the mth power and then taking the nth root, can be done in either order. All right, we could do the power first and then the radical, or we could do the radical and then the power. And then finally, anything to the first power is just itself. So a to the first will be a. These properties are going to be useful when we're simplifying power functions. In order to write functions in this form and seeing whether or not a and n are real numbers, and if it is a single term, then it is a power function. So when we do this example down here, we're essentially seeing if we can write each of these functions using some rules of or properties of exponents to see if we can write them as a single term with a coefficient and a variable and an exponent. Right? For example, if we take part C, for example, that doesn't look like a power function because there's a fraction. This down here kind of looks like a power function, right? 2s to the fourth. But the whole thing by itself doesn't look like a number times x to an exponent. But we can remedy that using the properties of exponents. What we can do is we can kind of separate this out and say this is 3 over 2 times 1 over s to the fourth. Right, we can separate that out and write it as a product. And then we can rewrite this 1 over s to the fourth using this property here, so that we can write the s to the fourth that's in the denominator with a negative exponent, and it will no longer be the bottom of a fraction. So we can rewrite this as 3 over 2 times s to the negative fourth. Now that we have it written like this, we see that this is the a, and this is essentially like our x to the n power, right? So we have something in the form of ax to the n, which means the answer here is yes. I guess we should write power function instead of yes. Power function. If it is, determine a and n. So a will be 3 over 2, and n is negative 4. Right? As long as you can identify what the a is, the coefficient, and what the n is, the exponent, then you have a power function. So for these problems, you may have to do some manipulation before you can identify what the a and n is. And the manipulation you do will be using the exponent properties. Any questions on that? Okay, I know I talked about end behavior last time, and I did an example of it, so I think you guys can continue working on that. I explained what inverse variation was. Okay, so I want to move on to 3.3 and talk a little bit about polynomial functions, their degree and leading coefficient, and then some of the characteristics of the graphs. This box here is important as far as polynomial functions are concerned. It gives you the standard form of a polynomial function. Was there another box? There's another box. Okay. A polynomial function is any function that has kind of terms. Each term is a power function with with a with the exponents being non-negative integers. So what does non-negative integer mean? Those are numbers 1, 2, 3. Oh, sorry, it could be 0 as well. Starting at 0, the exponent is 0, 1, 2, 3, 4, etc. Right? Those are non-negative integers. So that's what all of the exponents have to be for a function to be a polynomial function. And it's represented in this form where you have power functions added together with non-negative integer exponents. Each of the a's, an, an minus 1, all the way down to a2, a1, a0, those are called coefficients. And they could be any number, any real number. And then each of these terms, each of these little power functions is called a term of a polynomial function. So, determining whether something is a polynomial function or not, again, you may have to combine certain things using properties of exponents before you can answer that question. If we look at part C here, we have 5s to the 1/2 plus 2. This one is going to be is not a polynomial function. Who can tell me why it's not a polynomial function?
Because it isn't a whole integer, the exponent.
Good, since the 5s to the 1/2 term does not have an integer power. Right? The exponent on the s in that term is 1/2, which is not an integer. So that's why it's not a polynomial function. All right, next thing we're going to identify is a couple of vocab terms, the degree and the leading term and the leading coefficient. Those are three things we're going to define here and talk about. When we talk about general form, we talk about these exponents decreasing, so going down from left to right. So we usually put polynomials into this descending power order. So if we were to rewrite this polynomial up here in part B in general form, I would find the term with the biggest exponent and put that first, which is the exponent of 5. So I'm going to put this term first and then carry on going down to the next biggest power term, which is the negative 5x cubed, and then the x squared, and then the x, right? So now that I have this in descending, descending power order, I have this in general form. Once you have a polynomial in descending power form, then the degree of the polynomial is the highest power n. So in this case, the degree is 5 because the highest exponent that we see is 5. The leading term is the first term in the sequence, so the negative x to the 5th is the leading term. And the leading coefficient is the whole number, or the real number in front of the variable in that leading term. So if I look at this leading term, the number in front of the x is a -1. So then my leading coefficient is a -1. I know I did this for an example that's not asking for all of this, but you can do, well, I guess it's asking you to do that. So this example down here is asking you to do this degree leading term and leading coefficient for the functions up here that were polynomial functions. So you would need to do it for this last one because it's not a polynomial function. Okay, so that's how we find degree, leading term, and leading coefficient. Those are the three vocab words we need to have. As for the characteristics of graphs of polynomial functions, main things to note are that polynomial functions do not have sharp corners and they have no breaks. There'll be nice curves that continue on forever, either down or up at the extremities, and then in the middle they'll have smooth turns. They won't have any sharp turns and they won't have any breaks in the graph. There's a relationship between the degree of the polynomial, which if you remember is the highest exponent, highest power, the degree, and the number of turning points that a graph can have. And the relationship is that if you have a polynomial of degree n, we'll have at most n-1 turning points. Now that's a very simple statement, a very simple relationship between the degree and the number of turning points, but it leads to a lot of things. So if we think about this for a second, if I have let me just talk about this example up here. This function that's given to us here in the example has degree 4 because the highest exponent is a 4. So we have a 4th degree polynomial and it has 3 turning points. So you see in the graph of the polynomial here we have a turning point down here, we have a turning point here, and a turning point here. So anytime the graph goes from increasing to decreasing or decreasing to increasing, we have a turning point. Or you can look with your eyes and see that the graph turns at these 3 turning points. Now 3 turning points, or in general, anytime you have a even degree polynomial, anytime you have an even degree polynomial, so the fact that this is even is important, we're going to have an odd number of turning points. Right, because if the degree is even, then n is even, and then n-1, one less than that would be an odd number, right? So having an odd number of turning points means something about how the graph begins and how it ends on the left and right side. So if my graph goes up to infinity on the left side and I turn an odd number of times, I'm going to end up going back up in the end. Right, this is kind of foreshadowing into end behavior, but if a graph starts up here and it turns once, like a parabola for example, if it turns once, then it would just go back up, right? That's one turn. If we have 3 turns, we have something like this, where we turn 3 times and we end up going back up again. If it turns 5 times, 1, 2, 3, 4, 5, it is again going to end up going back up. So whenever you have an even degree polynomial, it's going to have an odd number of turning points, meaning it's either going to go up on both endpoints, or if the graph started down here, going down forever on the left side, and I had 1, 2, 3 turning points, or any odd number of turning points, it's going to end up going down forever again on the right side. So end behavior is totally determined by the degree of the polynomial, which determines the number of turning points you have, which determines the shape of the graph that you have. Do we have anything? Okay, last thing I want to define here so that we can talk about things is we'll use this little corner here. So make a little box here for yourself. Since there's no other room. What is it called? Classifying polynomials by number of terms. With the number of terms, 1 term, 2 term, 3 term, and 4 term, I guess we should say terms. Some of these have special names. So a 1-term polynomial is going to be called a monomial. A 2-term polynomial is going to be called a binomial. A 3-term is going to be a trinomial. I guess I should call this last one 4 plus terms. If you have 4 or more terms, we just call it a we just start calling them polynomials at that point. You can be more specific and say like 5-term polynomial, 6-term polynomial, but in that case, the name, there is no special name for them. It's just called polynomials, and you just name the number of terms. Do another box here. We can also define polynomials by their degree. So classifying. Is this gonna come up? I feel like this should be a thing that's in the Spark book. End behavior, graph a polynomial, rational. Okay, so I guess we didn't classify these. Classifying polynomials. These are tools you should have by degree. So the highest exponent in a polynomial. Also, they have certain names. We'll do a little table here for this one. Oops. And then name for a 1-degree a polynomial, where n is 0, will be a constant. If n is 1, we have a linear polynomial. If n is 2, we have a quadratic. which we've kind of talked about quadratics. If n is 3, we have a cubic polynomial. If n is 4, we have a quartic polynomial. And this does continue into 5. 5 is quintic, it's not really used that much. And then 6 and on, you would just say 6th degree, 7th degree polynomial, and so on. So the first few have special names, just like the number of terms classifications. And then after that, we just call them by the number, by the degree, or by the number of terms that they have. Okay, you have some examples that you can work on in the end of section 3.2. Go ahead and finish the end behavior examples at the end of section 3.2, and then go over the examples in 3.3 that I didn't do in your groups. There's also a worksheet on Canvas. So the worksheet on Canvas looks like this. It's a little bit different this time. We are going to, there's a fill in the blank at the top that I'm going to help you with right now. And if you wanna print this out or pull it up, you can do it once I send you into your groups. But make note that the first fill in the blank, which we didn't really cover, well, we did, but we covered it as far as like the number of turning points that a graph has. An odd degree polynomial will have at least one real zero. The rest of it, one term, two terms, three terms, number 5 is going to be even degree polynomial, and then the rest you should be able to fill in the blanks for. And then there's a nice table here where you're given some polynomial equations, maybe not in their standard form. So you're going to put them in standard form. We also called it general form in the notes, right? General form, standard form are going to be the same thing in this case. So you're going to put this in standard form, like we talked about. You're going to name the degree. You're going to classify by degree, classify by number of terms. LC stands for leading coefficient. And then end behavior you can not do yet. We will do end behavior next time, and you can fill out that last part on Monday. So you can fill out pretty much this whole table except for the end behavior part for now. Leave that alone. And then you can also not do the second page until we talk about end behavior. So you're working on the first page of the worksheet here. Don't worry about this top corner. Don't worry about your period. Don't worry about the date really either. Just work on the problems on the worksheet, and don't turn it in today because you can't finish it today. It's not due until Monday.